This one sponsored very kindly by Scale Up Systems.
Very important to understand the impact of scale-up on the outcome of the process. It was also, I wanted to be able to develop a process where I could explore what would happen if I used different types of equipment, different equipment modes, different setups, ideally without having to either buy new equipment or to have to set large-scale trials in place. And finally, it was very important to be able to share the knowledge that had been gained with colleagues to help them deliver first and ongoing campaigns with the yield and quality expected. And I would say that you can only really hit all of these outcomes with the support of a kinetic model. And in relation to the title of my presentation, when I talk about late stage scale up, I would argue that you can start to develop a kinetic model as soon as you have all of your main reaction components decided. If you know what reagents you're going to use, what ideally what solvent or solvents you're looking to use, catalyst that you're going to use, that's the right time to start modeling. And I think the other key trigger for kinetic modeling is, as my colleague Wilfried Hoffman put it, when scale up is on the horizon, when you're starting to think about what's the closing timeline to scale up your process. And this is based on a case study from AbbVie, specifically James Marek and Eric Moschetta. And here it was looking at using the predictive power of models to very quickly and accurately understand failure modes in a CDI coupling reaction. So in this case, we had a desired reaction where CDI was reacting with this TFVA, this amine, to form an activated complex, and that was then going to go on to react with another reagent. But there was also a competing overreaction of the activated complex to form urea, and this was undesired. And so the aim was to maximize the formation of the activated complex and ideally avoid urea formation. And in this case, because we had, or because there was products that were actually quite difficult to see and quantify by techniques like HPLC, the reaction was actually monitored by online mid-IR. It was also quite a fast piece of chemistry, so mid-IR in situ monitoring was more effective and easier to institute than offline sampling. But this does point to one of the important features of kinetic modeling, that it's always important to collect the right data and good quality data. And so there's no one type of data that is right, that can be said is right for all reactions, but it's always worth looking at what is the best data that you can use to quantify the consumption of starting materials or the formation of products in order to deliver your model. So in this case, they ran an initial experiment and monitored the depletion of starting materials and the formation of products by IR, and the dots here, the red and blue dots, indicate the experimental data. And then they built a model based on this two-step mechanism and tried to fit the experimental data. Now, as you can see, the fit is not that great. It indicates too fast a reaction at the start and then too slow at the end. And this was postulated as being as a result of an autocatalytic effect. The imidazole was playing a role in the reaction. And this hypothesis was tested. They added some imidazole, and immediately they saw that the induction period disappeared. So as a result, they were immediately able, based on this one fitting experiment, to build a new model with an additional catalytic reaction step. So now they were saying there was a non-catalyzed reaction, a catalyzed reaction, and then the overreaction. And when they then tried to fit the data based on this three-step mechanism, they got much better fitting over a range of temperatures and other reaction conditions. And using those fits, they were able to determine rate constants and activation energies for all of the reactions. And when you get values like this, it's always worth doing a bit of a reality check. And I think key here was that the activation energy of the catalyzed reaction was noticeably lower than that of the uncatalyzed reaction. So in this case, what we're seeing is that on the basis of very few experiments, kinetic modeling identified a new reaction pathway, and this understanding was critical in helping to avoid or to know about potential failure modes when this was moved to larger scale, and it delivered much greater process robustness. And you can see you can build the reactions using structures. You can look at the whole reaction scheme in one go. So it's much easier to be sure that you've set the model up effectively. You can write in all your reactions, and then if you've got a more complex system, which isn't a pure batch system, it can be you can very simply add in feed tanks, add in solid phases, whether they be dissolving or precipitating solids, or you can add immiscible liquid feeds. And then with that, you can simulate model outputs, you can fit experimental data, you can do optimization studies. And what I'm going to show you here is an example of a full factorial design. So in this case, this is a reaction of aniline and benzyl chloride. And you can see that this is going to show how you set up a full factorial design with a range of temperatures and a range of starting quantities of benzyl chloride. And in this case, we've got 21 levels of each, which would require 462 experiments. We're going to look at how that impacts on the yield of the product. If we go up to the top left-hand corner, this is the highest yield. So this is showing we've got a high yield here, lowest yield at the higher temperatures,